Hello, hi everyone. Hope you are in good health. So this video is for the chapter 3 part 2 and a little bit on the chapter 4. So let me share with you the slide. I would like to continue from the previous video or previous slide. We are on still on the image enhancement, but uh, this time is for the frequency domain. So what is enhanced to make greater as in value, desirable or attractiveness? Frequency, the number of times that a periodic function repeats the same sequence of values during a unit variation of the independent variable. So for this time, we are going to have the image enhancement in the frequency domain. Okay, before this image enhancements in time domain, but now in frequency domain. So in frequency domain, we are focusing on the Fourier series. So this is just like a revision from what you have learned in other subjects on 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 this Fourier series. So we have a Fourier transform. So this is the history. I don't want to go detail. So this is also about the Fourier. It is actually applied to the signal. So we have a periodic signal like this. Then when you apply Fourier, you will get the frequency component of the signal. So it's same concept goes to the image because image is also signal, but in two-dimensional form. So this is the periodic signal. So we can apply Fourier to analyze the signal. So if you look at the Fourier, Fourier is very powerful. It has been used in a lot of application, including application in industry. Some of the oscilloscope, if you want to check a signal, electrical or electronic signals, you have a very special button or features where you can just choose to see the signal in Fourier. Okay, so it has been used in many scientific areas in physics, signal processing, probability theory, statistics, cryptography, acoustic, optics, and etc. Um, Fourier transform in signal processing, for example, in audio and also image signal processing. Audio and image signal very alike. Audio is 1D, image signal is two-dimensional. Both can be continuous or discrete digital. Some kind of filters can be used. So Fourier transform is used for easier way to apply different kind of filters to the signal. Filters are used for removing unwanted frequencies from signal, removing noise from signal, alerting signal somehow. So this is a type of Fourier series or Fourier analysis. We have a Fourier series, Fourier transform, discrete Fourier transform, fast Fourier transform. So this is the theoretical. You learn this detail theoretical or derivation of the equation Fourier series in other subject, especially in signal processing. But when we apply Fourier in image, so for example, if we have this image, one dot here, you apply discrete Fourier transform, then you get this output. Okay. So this is another example. PCB scanning electron microscope image of an integrated circuit magnified 2500 times. So you can see um, the defect here or soldering leak. So this is the output. okay, in image. I mean, you apply Fourier to the image, you get this output. Okay. So there is also inverse discrete Fourier transform because if you use um, Fourier for image enhancement, then to get back the enhanced image, we can use inverse discrete Fourier. So basically, this is the general process of Fourier or image enhancements in frequency domain, pre-processing Fourier transform, filter function, inverse Fourier transform, post-processing, then we get enhanced image. I don't want to go details on this one, okay, but I repeat again, when you have this image, you apply DFT, then you get this output. So uh, in frequency domain, or if you apply for Fourier series or discrete Fourier transform or fast Fourier transform, you get this kind of output. So it is important to understand what is the meaning of this dot so that we can continue to analyze the output of the uh, Fourier. Okay, so this is another example. So this is the detail of example simple calculation. X matrix 1 vector 1289. Then you can apply the FT to this value. Okay, so this is more I mean, how to say, it's not the uh, theoretical or calculation of the Fourier, but this is more to interpretation of output of the FFT when we apply to the image. Okay, so we understand that image in a form of matrix, row and column. So if we apply FFT 1D, one dimensional, this is signal, is more signal processing. Uh, we get the frequency component. Okay, frequency component. We can apply FFT 1D to the image, but it is not practical because if we have this image, for example, then we need to have to take a sample to apply for one dimensional. But if we just take this one, it is not represent the whole image. So it's not practical. Okay, then we apply FFT 2D. There is a specific Fourier for two-dimensional FFT 2D. So we can just apply directly to the image without need to take the sample one by one. So this is the formula. But again, we are not going to go details to look details to the calculation from the Fourier equation, but the important is how to interpret the output here. So this is the interpretation. If we get this output, then the middle center here represent low frequency, and and at the edge represent highest frequency. So this is the example. We have this image. They will apply, then this is the output of the Fourier. Then we can interpret in terms of the frequency based on the this definition. Okay, so I just skip this one. So this is the example how FFT can be used for image enhancement. This is the image with noise. So not look good. We want to get this output. Then by applying the Fourier series, we get this spectrum. Then apply filter. Then apply inverse Fourier transform. So the final image, the output image, is now enhanced compared to the original image. Okay, so this one you can by your side. So basically, this is the general step. Okay, we have a pre-processing, Fourier transform, filter, inverse Fourier transform, then you get the enhanced image. Why Fourier transform is useful? Easier to remove undesirable frequencies, faster perform certain operation in the frequency domain than in the spatial domain. Okay, so this is another example. Okay, so I think that's all about the Fourier. So now is filtering. So this one you can just look at by yourself, high pass filter, low pass filter, right? So on and so forth. Okay, so I think that's all for the chapter 3. We go to the chapter 4. Now we look at the color processing. Okay, so chapter 4 is more to the next step after the pre-processing, enhancement, removing noise, region of interest, segmentation. Now is image processing. We want to get features of an image, then we process the image. One of the method to process an image is color processing. So this is the example of coding where you can get it from MATLAB, right? Color fabrics, okay, to distinguish the color of fabrics so that easy for operator to check to do the quality inspection. So what are digital colors? What are color space? Why do we have different color spaces? So the colors that humans and cameras can see are determined by the nature of the light reflected from an object. Green object reflects green objects reflect green light. So what is colors? Achromatic, only intensities, amount of light. Gray levels as seen on black white TV monitor, range from black to white. Chromatic, light wave, visual range 400 nanometer to 700 nanometer. So this is the spectrum of the wavelength. So the color that we can see is actually fall under this spectrum from 400 nanometer to 700 nanometer. So red, green, blue, this is a common color in image processing or called primary colors. RGB were chosen due to the structure of the image. RGB is normally used a lot in digital cameras. Okay, so this one I think you can read by yourself. We have additive or subtractive colors, sum of light, additive colors, sum of light of different wavelengths that light reach our eye directly. Example, TV multimedia projector. Subtractive color, what color is emitted by the sun and is only partly reflected from object. Red paint filters all light except red. Yellow paint absorbs blue but reflects green, red and green. Example paint. So this is the RGB color space. So if you have this combination of R 255, G 0255, B 00255, then you get a certain color output. So this is the color space. You have R, you have G, the 60. When you combine these three, then you get final pixel in the image. So we have also CMYK and CMYK color models. Exercises, how many different colors exist for a 24-bit pixel? This is the example of RGB. So the RGB can be converted into color to grayscale. So RGB format of image converted into grayscale by using this formula, or this formula also can be used to get the grayscale. Conversion of color image to grayscale, convert to luminance value for each pixel, y equals r plus g plus b divided by 3. This is a simpler technique, but the resultant image is too dark in the red area and too bright in the blue areas. So in order to solve or to overcome the problem, the conversion method use weights y equals WRR, WGB, WBB. So there is a weight that can be used to convert from color image to grayscale. So this is an example of a weightage for each channel of R, G, and B. Color thresholding for a certain image processing or object detection, we want to detect a certain color, so we can use a color thresholding so that we can remove other color. So this is a color thresholding normalization of color threshold. Instead of using a normal direct thresholding of color here, we can normalize by using small R. Okay, so this is example you can do by yourself. We also have the other component of color, HSL and HSB. Convert SR, you just apply the formula. So this is the exercise. Okay, so I stop here. We continue the next video on the part 2 of chapter 4, color processing. So till now, see you again. Thank you very much.